Hello, everybody. Thank you for joining us today, and welcome to this month's IDQ Quantum Technologies webinar. I'm Tyle Stelzig, a product manager for Q Sensing at ID Quantique, and it is my pleasure to introduce today's esteemed speaker, Dr. Michal Parniak. Dr. Parniak is a leading experimental physicist in quantum optics. He joined the Center for Quantum Optical Technologies at the University of Warsaw in 2020 as a group leader after a postdoctoral stay at Quantop at the Niels Bohr Institute at the University of Copenhagen. His research interests cover a range of topics in quantum optics, such as single photon detection, optical quantum information processing and communication, atomic ensembles, nonlinear optics, and quantum optomechanics, and most recently, the topic of today's talk, Rydberg atom physics. Within QOT, he developed experimental implementations of protocols designed by the theory groups and maintains close collaboration with Professor Wasilewski and Professor Poljic of QOT and the Niels Bohr Institute in Copenhagen, respectively. His significant scientific achievements include demonstrating super resolution in imaging using two-photon interference and demonstrating record-breaking capacity in a quantum memory, as well as the first demonstration of entanglement of macroscopic spin and mechanical systems. Today, he will be talking about his recent work counting microwave photons through upconversion based on Rydberg atoms. We are very happy to have Michal with us today, and we hope you enjoy his talk. Just to mention quickly before we begin, we will be recording this session, and the webinar will be available for rewatching shortly after the session concludes. We will also have a few minutes for Q&A at the end of the talk. So throughout the talk, please feel free to type any questions into the Q&A chat box at the bottom of your screen, and we will filter through these questions and answer at the end. Any we don't get to, we will follow up offline via email. So without further ado, Michal, the floor is yours.
Thank you so much, Tyle, for the introduction. Many thanks to ID Quantique for organizing this excellent platform for our today's exchange. So welcome. I'm broadcasting here from University of Warsaw, from our lab. And today I'll be talking about one of our most recent experiments. This experiment is part of our so-called international research agenda, which is the Center for Quantum Optical Technologies, established as a 5-group center of excellence led by Professor Konrad Banaszek and financed by the Foundation for Polish Science. So before we begin, you got a wonderful introduction about me. I always would like to also follow up with the story from my point of view. So I also did the PhD here on cold atoms. I actually started with hot atoms and started doing cold atoms and started doing hot atoms again. Now I'm doing both. In general, those atomic ensembles have been my point of interest all along, and in about 80% of experiments, I've been also doing the photon counting. So this was also the case during the PhD and a little bit before during masters. In Copenhagen, we did experiments both with homodyne and photon counting using atoms and quantum optomechanical systems, so tiny membranes based on silicon nitride. Most recently in QOT, which is a new enterprise, we do also both, and as you will see even during today's webinar, I will present some results from photon counting and some results from coherent type of detection. So our motivation today is a pretty popular topic explored by many groups, and I'm not gonna cover everybody's achievements today, but in general it would be really great to have quantum networks, but not only for the quantum secure communication, key distribution, but also to be able to connect quantum computers with each other. So it is a very far-fetched goal. If we want to do that, we need to be able to convert a qubit that lives in a quantum machine that can be operated on, that can interact with another qubits, into preferably an optical photon that can travel far away in a fiber, and that can also use, for example, quantum repeaters to travel even at very long distances. So the challenges here are numerous, but one of the overarching ones is the conversion, both two-way conversion really, of microwave photons into optical photons, which are good in networks. So here the example of wavelengths that I'm giving here are really the ones that we'll be talking about today. But in reality, probably the highest kind of achievement would be to be able to use the telecom C-band for light and about 5 gigahertz for superconducting qubits. On the other hand, microwaves are also great for interacting, for example, with trapped ions. So it is not only about necessarily superconducting qubits. So this would be a very far-fetched goal for which we would actually need to do it with pretty much 100% efficiency and no added noise. So we cannot add any noisy photon here. And this is a far-fetched goal. So we've been thinking, can we use the quantum transduction skip of that sort in a more immediate application? So kind of, one could almost say noisy, it's not exactly intermediate scale, right? It's just near noisy and near term. So can we take some microwaves, maybe put it on an antenna, maybe put it directly on our atoms and upconvert it to optics and make use of it? So indeed, it turns out that this has many potential applications. One of them is just being able to receive those microwave photons with greater precision. And you can consider then counting those photons, or you can consider coherent detection of the photons, like beating with a local oscillator. And in many cases, it turns out that yes, indeed, we can avoid many difficulties that are present in microwave circuits by putting the optics somewhere at the very end. And that becomes even more apparent when you consider terahertz waves and the ability of the atoms to be able to sense terahertz waves in a similar way as they can sense microwaves. And the terahertz waves are very difficult to work with. And if you can use the same device for many orders of magnitude of the frequency of the electromagnetic wave, that would be amazing. So this transduction will be concentrating around atoms, but it's not immediately clear how you would use these atoms. One example is to take, let's say, famous rubidium atoms, which will have a ground state splitting in the microwave range. So, for example, for rubidium-87, that's 6.8 gigahertz. Unfortunately, this kind of lambda type system, while it can be very nicely used to convert this to, for example, absorb this microwave, absorb this photon, and then emit this photon in proportion to this microwave. So that can be done, but the dipole moment here for the free space atom will be very, very low, because in all cases that we can work with, this is a magnetic dipole transition, a very low dipole moment, much lower than actually the optical transitions. So maybe going to ions is a solution here, embedding them in cavities. This is a whole big story. One of the rapidly developing fields is the so-called various combinations of optics, electrical resonators, and mechanical resonators. The idea for the transduction here is that you take an LC circuit in which the capacitor can be simultaneously part of the circuit and part of an optical cavity. So now, if you can do that, that doesn't really yet do anything. The capacitor also has to move, so it has to be an excellent, actually, mechanical resonator, and then it can transduce one single excitation, single quanta, between optical photon, mechanical phonon, and a microwave cavity microwave photon. A very complex experiment, but certainly extremely fascinating. You can try to eliminate the mechanical part by using electro-optics. That is then becomes quite a material science as well. You can also try to use magnetic effects, so not necessarily crystals that respond to the electric component, but materials that will respond to the magnetic component of the electromagnetic wave. But we'll be working with atoms today. So as in the previous case, the mechanics was the intermediary, for example, between microwave and light. Here it is the atoms. And we select Rydberg atoms because of their extremely favorable dipole moments and the very existence of the microwave or terahertz transitions between high-lying states. So often there are many famous experiments in which we excite cold or hot atoms to a Rydberg state, observe, for example, Rydberg blockade, and many fascinating effects. Here we'll be using more than one Rydberg state because between two Rydberg states, let's say, we'll be using 55D state and 54F state. So those have a very nice dipole transition between them, the electric dipole transition, with a huge dipole moment. So now if you can design a nonlinear mixing process, just like in conventional nonlinear optics, that goes around resonant energy transitions in the atom, then you will have a huge nonlinearity that will allow you to, for example, absorb a microwave and emit an optical photon. So this was done recently in the, still quite recently in a cold atomic ensemble, and even more recently, the group of Jonathan Simon in Chicago now moved to Stanford. They used they built a very complex machine in which it is only a 4-wave mixing process, as you can see here. So we absorb the single 780 photon from an optical cavity. Then we bring it up with the 481 nanometer laser to a Rydberg state, which allows an emission of a 3 millimeter, so it's a 100 gigahertz, a 3 millimeter wavelength photon into a millimeter wave cavity, followed by an induced emission in the ultraviolet range, which needs to be driven by the laser. That is quite challenging to take the entire cryogenic setup. Here it's a superconducting cavity, and also add to it a UV laser. So a challenging experimental endeavor. But nevertheless, it's not that different from quite complex optomechanical experiments that I'm showing here as an example, where again the mechanics is an intermediary. So in this experiment, for example, a single silicon beam was used simultaneously as an optical photonic cavity and a mechanical phononic cavity for the common interaction with a sound wave that you send into the cavity. And in fact, to be even more kind of close to the conventional example, in Copenhagen, our new neighbor group of Albert Schlisser is working with membranes that will be able to interact both with a microwave cavity and an optical cavity. So this is an example of the microwave cavity interaction. I have personally worked with those silicon nitride membranes that can interact by being placed in the membrane in the middle style inside an optical cavity, also in a cryostat. So it's a nicely developing field. But coming back to the Rydberg atoms, they are actually extremely useful, even if they are not yet brought into the quantum regime. So it's been discovered that they are a very nice way to sense Rabi oscillations. So Rabi oscillation in a two-level atom is a really simple example. If you have two levels and we apply a resonant field between them, then the occupation of those two levels will oscillate in the assumption of no decoherence. will oscillate at the frequency known as the Rabi frequency, which is proportional to the amplitude of this electric field applied here, of this wave, times the dipole moment divided by h bar. So a simple effect, but how do we observe it? Those could be really fast oscillations. And there are many ways, but we are able in the atoms to observe it spectroscopically. So we use the effect of the electromagnetically induced transparency. And normally, if you take this three-level atom where the upper level R1 is a Rydberg state, you will see an absorption profile due to the probe absorption between levels G and E, and a dip, which is called the electromagnetically induced transparency. So it is always nicely said that the dip appears because of the destructive interference of two paths of the probe absorption. So it can either be absorbed directly or via the Rydberg state. If those two probabilities interfere destructively, we get a dip in absorption, which is the transparency window. But if we apply the microwave between those two levels, so you can think about the R1 and R2 as the original G and E levels in the Rabi oscillation scheme, then we can see that this EIT dip, the window, is split exactly by the amount of the microwave Rabi frequency. So this is not the frequency of the microwave, it's Rabi frequency, proportional to the intensity of the microwave. And that amazingly provides, even in a very simple vapor cell setup, a way to calibrate the intensity of the microwave or a terahertz wave that you are applying to your cell, as long as you know the dipole moment. Fortunately, it can be calculated with a rather nice precision. And since this discovery, which is a simple effect, but it's amazing that it works even with the vapor cells, so just the room temperature atoms. People have been working on many practical electrometers. So, for example, you can put a waveguide into the rubidium vapor and see a very strong interaction already close to this waveguide, so you can be sensitive to really small fields. You can think of making very small vapor cells. You can think of fiber connectorizing them. So this is actually a picture from Copenhagen where it is actually a magnetometer, but the vapor cell magnetometers are also a really huge topic, and it's really exciting to think that we can also make now those things with microwaves up to terahertz waves, or maybe even small frequencies, but that's usually less of a problem. So with these exciting applications, it's interesting to think what kind of exploration can we do to really reach ultimate sensitivity. And that's where we come in. So we made the first transduction from microwave into the optics using a vapor cell setup. So you would think that how could this work in such a noisy system? But we, for the first time, presented that indeed we can go down to really low levels of the microwave and still see the very pure signal of the conversion. And compared with, for example, the experiments that I've shown before, here we are neither using an additional microwave, which could spoil the result because it's too close in frequency, and neither nor we were using a UV laser, which would be extremely difficult to work with those glass cells. It's always a problem. So this is done by using a 6-wave mixing process and lasers that are all at reasonably comfortable wavelengths. So you can. So our work is on archive, and very soon it will also be published in just a few days, actually. And the setup is not too complex. The vapor cell is in the very center. It's surrounded by the microwave absorbing shield. It's very, very poor, you would say, a simple but sufficient anechoic chamber in a way. And then we just apply all those lasers from the proper directions such that some of the Doppler broadenings are cancelled out. It's a really broad topic how to do it optimally, but we found a way, and that increases the efficiency. And our setup around that needs to consist of a microwave generator where we split off a small amount and calibrate using a commercial spectrum analyzer. The laser setup where we take our lasers, which are at weird wavelengths, and use cavity transfer logs to log them to a stable frequency reference. Our cell, which is actually in a plastic 3D printed holder, such that we don't disturb the microwave field with metallic elements, and the detection. And the detection is now the important part, because we really were first for this one to use single photon counting. And that's where also ID Quantique also nicely plays in. I will tell a little bit more about it in a moment. And the measurements that we do here consist of the following. We can either measure photons directly, just do the intensity measurement. We can do some additional filtering using cavities, because normally we only use simple broadband dichroic mirrors, or we can look at autocorrelation, so the G2 of the emitted radiation. And so first we start with a little bit of optimization. We optimize the tuning of the lasers, and we see that we have some understanding from the simulation and control over how this behaves. And we can predict also some 2D maps in terms of the tunings of various lasers. And later we put the system to the real test. So we start with a big intensity. So this microwave intensity, around 1 milliwatt per meter squared, is so high that it actually induces the significant Rabi oscillation. And the splitting that I've shown is actually called Adler-Towns splitting. And in this regime, our converter is saturated. So it already loses the efficiency. And here, I'm not yet giving you the total efficiency. This is relative to the maximum. The actual efficiency is quite hard to define in a way, because it's a free space setup. I will tell about it if you have some time. But we start with this huge intensity, and we go down in the power until we hit a plateau. And now this is amazing already, because this is 6 orders of magnitude in the intensity. So we have to put some into so this sometimes could be already too many photons, of course. So we put neutral density filters, and this saturation allows us to calibrate what is the microwave electric field here. And on the other hand, when we hit the plateau, we had a strong suspicion already that this is the thermal noise, because we are in room temperature, we are in a black box, so we should be seeing the black body photons. And indeed, it turns out that the calibrated amplitude from the splitting and the calculated intensity of the black body radiation noise fit really well, so they give a consistent result. The sources of the noise here are still a little bit technical. For example, we have some fluorescence from the glass of the vapor cell, but essentially we are able to detect photons with a really good precision thanks to the nanowire detectors. So they are actually in a different room, in a nice closed-off cabinet that we built around our setup. And we really benefit here both from the fact that we have more than 80%, 85 to 90% efficiency, so that's very convenient. But for that we also get less than 1 Hertz dark count rate, so this becomes completely negligible. It wouldn't be negligible with the typical APDs. And as I will show in a moment, we also actually need great timing. So we would think, why? Because I mean, it's a narrowband atomic setup, but actually we take also advantage of the timing. So this is some today's pictures. The setup is actually usually in the black box operating, and we use also the ID 900 time tagger. So a little bit about this thermal noise. So we go back to really thermodynamics 101. We look at what is the intensity of the electric field in a box, but with a correction such that not all the waves standing waves in a box will be upconverted because of the phase matching condition, as in typical nonlinear optics. And this phase matching condition can be must take into account all the driving beams, their Gaussian shapes, even the Gauss phase, and the polarizations. So this relative efficiency gives us, in a way, a profile of our antenna, and this profile, when integrated, allows us to estimate the total noise that we should be observing. So now for the timing and bandwidth issues. So our converter has a bandwidth. It converts a narrow band of microwaves. We can do that. We can check that by scanning a microwave tone in a frequency and seeing that, yes, okay, so we have a peak in the conversion. Conveniently, we can also tune up the lasers to effectively increase the workable bandwidth. So that means we can kind of shift this instantaneous bandwidth peak around. And the theory predicts this effect quite well from the Doppler broadening. But if we have this bandwidth, that means that we can also have the autocorrelation function of the upconverted thermal radiation, because if the thermal radiation is basically a white noise on this scale, and if this part of the thermal radiation gets upconverted, it should have the G2 connected with the stochastic process, the stochastic G2 connected with the G1 that's given by the Wiener-Khinchin theorem, where the S of omega is the bandwidth that we just measured. And the G2 will be 2 at 0, and then there will be a factor stemming from the thermal G1 and some coherent wave that we also put in at the same time. So this is a little bit different from doing the heterodyne measurement, where we put an additional LO at the same frequency. Then we see that the bit note is a bit broad, but this is just due to the lasers not being locked perfectly and having some phase noise. But now for the photon counting part. So we were really happy where we do first about an hour-long measurement, and then a peak appeared. This was way before optimizing the setup, and the peak appeared at the 0 delay on our ID900 time tagger, and we've been able to see, okay, this is a strong indication that there is some bunching. The bunching connected with the thermal state, and when we took more data, zoomed in, etc., then we've been able to observe a really nice thermal signature. And the theory here really comes from the Fourier transform of the bandwidth, so the proper Wiener-Khinchin theorem, G2. So we find quite a nice agreement here, and we are also able to do some tricks with that. So for example, this is an interference of the thermal radiation, the upconverted thermal radiation, and an off-resonant coherent microwave that is also being inefficiently upconverted. And then we get bit notes in the G2, and we are able to predict it really nicely. So as you can see, we have pretty fast bit notes here, so having a good time tagging resolution is quite crucial to obtain this kind of results. So this is the kind of 1 nanosecond resolution here is important. We have a resolution of, given the jitter of the nanowires, it's about 50 or less nanoseconds. Sorry, picoseconds. So this is more than enough, but not so far, right? So now we can also put a microwave tone on resonance and see that if we put more coherent states, then our G2 becomes closer to 1. We can predict it using a quite general theory. As the final part, we've been able to show that indeed we can also cover all the combinations of those lasers to see where the noise is coming from. And after quite some optimization, we see that indeed the dark rate is almost none, as also the influences of some other lasers, and only there is some fluorescence in the glass and other optical elements induced by the blue laser. It's 480. It's not so energetic, but it still induces some fluorescence. So we believe that this is a good step towards towards making really amazing atomic antennas, where we use either a photon counter or another device to detect microwaves with really excellent resolution, and to also detect terahertz waves to be able to see thermal radiation. So this can be a bolometer, an imaging camera, and many other different devices. Possibly also not just being shined on with the microwave directly as here, but coupled with a cavity and the microwave antenna. So this is a sketch of the future where we can further make it a port coupled system and really increase the efficiency. We are also strongly working on our heterodyne detection scheme, which conventionally has used an additional microwave to induce the bit node, but we are now observing this bit node without an additional microwave because we are able to close this loop here just using lasers. Very recently, we learned using many of our different tricks to cancel out this 80 kilohertz line that I have shown you before using a nonlinear crystal. So using a mixing process in this crystal, where we are able to measure and cancel out the phase noise of the lasers down to a line that is basically 1 hertz in line. So having an all optical super heterodyne receiver. So thank you very much, and I hope you also enjoy the future applications ranging from really precise detection of various kinds of radiation to even imaging. And thank you for the team and our funders. Yeah.
Michal, thank you so much. That was a wonderful talk. I really enjoyed it. I'm sure our audience got a lot out of that as well. Yeah, it's exciting work on an important question. Yeah, of course, at ID Quantique, we're always happy to see our detectors used in great science like this. Yeah, so just as a reminder to the audience, we do have a few minutes for questions. So please enter any questions that you have in the Q&A box, which you can see at the bottom of your screen. So just on the banner below Michal's slides in the Q&A box, type in your questions and we will answer as many as we have time for. Those we don't get to, we will respond to you over email. So just to get us started, as I see some questions starting to come in, I wanted to ask something. So in this talk, you presented on conversion from the microwave into the near IR, and I was wondering about whether it would be possible to do something similar for the telecom band.
Yeah, it's a very good point, because the near IR is one of the multi-mode telecom bands, but it's really not that great. It has about a 3 dB loss per kilometer. It's not horrible, but not great. And so for networking, it would be nice to use telecom. And to do that, we would just need to select a different transition here. And we're fortunate enough that in rubidium or also cesium, you can find one, and then you get photons at, for example, 1530 nanometers, a perfect telecom band. And yeah, I think actually the detection then becomes even more crucial to have really nice superconducting nanowire detectors, because you still need the good dark count rate to be able to detect those. So yeah, I think it is a very interesting future direction to also upconvert a little bit less just to telecom. So it's less, but it's practically a little bit more challenging, because we will not be able to see all our beams. But yeah, a good point.
Yeah, thank you. That's great to hear. So yes, there are some other questions coming in here. So one question is, can this be extended into the terahertz range?
Right. Yes. So the specialists in the terahertz range is currently a group in Durham, So I certainly recommend this paper. However, the detection of the terahertz waves using Rydberg atoms was an incoherent type of detection, so it was a change in fluorescence. I think it would be really cool to go towards also upconverting terahertz waves of various kinds. And for that, the trick is you go a little bit down with the Rydberg level, and then the transitions become more far apart, but still nice dipole moments, sorry. And you should be able to also upconvert many different terahertz transitions. But the trick with the atoms is always that you kind of get a really big range, but of still kind of narrow band transitions. So you get a big selection, but not the full spectrum. However, it can be a very useful tool. And yeah, the one trick with the terahertz is also you need to take care of what is your cell made of, because some of the glasses will just absorb the terahertz wave.
Great. Thank you very much. A somewhat related question from Florin Cabrera Fernandez. Would you please comment on high energy microwave electron entanglement? Is there an analog for high terahertz communications with the laser photonic single photon detection? He says, I think from your last slide, you're showing microwave to optical conversion, and then is it possible to implement in terahertz as well?
Mm-hmm. Right. Is it enough for high terahertz coming with the laser photonic single photon? So high terahertz, I imagine this is like the going into really high energy terahertz, like several terahertz. I can predict, and the trick with the atoms is that we currently do not know. So yes, we already know that we can absorb some terahertz photons. We don't know what will be the bandwidth exactly there. How can it be manipulated? And while interesting, I'm not yet sure whether we'll be able to achieve bandwidth that is actually useful for communication. On the other hand, it seems that there are many tricks to extend the bandwidth a little bit at the cost of sensitivity, but maybe not that much. So that some things remain to be seen. So yeah, I think that this is all I can say on that at the moment.
Great, thank you. This is, yeah, so interesting from Frederick Overney. With what accuracy can the dipole moment be determined?
Oh, yeah, good question. So so there are big theory papers and packets that help you do that. And I don't think I want to comment on the exact accuracy. It is in the certainly less than some percent range, but this is what we observe consistently. I can tell you that those same tools also predict the frequency of the transitions, and they are quite precise, but sometimes we find practical offsets, for example, due to collision shifts. So that could also affect sometimes the dipole moment, so we need to be careful. And I mean, this is all in the much interest of institutions such as NIST. So so using it as a calibration device. So it is quite certain that this will be a topic of interest in the near future and currently.
Great, thank you. Let's see. So here's so from Mohammed Khalifa, nice talk, thanks. How do we envision the microwave cavity to be implemented? Is this a superconducting cavity? Is it room temperature? And what about noise?
Yeah, so it would be amazing to have in the future a cold cavity with cold atoms. Becomes a little bit closer to the fundamental achievements published in the Nature paper this year, right? But if you this one, if you use a microwave cavity in room temperature, you can still enhance your measurement precision by the amount of cooperativity of this cavity. So it doesn't hurt you that much that the cavity also increases the thermal noise, because the process is cooperative, so you're able to measure and in a way predict some behavior of this thermal noise. So it becomes a really interesting playground for the various quantum estimation methods applied in the thermal environment. You could, for example, imagine that this process actually removes microwave photons. So it would be able to some degree, cool the microwave cavity using, as in a sideband cooling experiment. So that remains to be seen. There are some practical challenges with those cavities, like putting the glass inside the cavity, for example.
Great. Yeah, so there are still a couple of questions we haven't gotten to, so we will respond over email to these last ones. Let's do just one last question, and then there will be a quick poll that my colleague Catherine will share. So just a final question from Alok Singh. If we modulate the RF, can we detect the modulated data with the optical field?
Yes, yes, and that's very cool, right? So now you can think of various intensity modulation, phase amplitude modulation. Sure, I think it will be fascinating soon to implement various more advanced schemes, some like QPSK, many more PSK, etc. The phase shifting, and interestingly, there are some tricks here that we can use a microwave local oscillator and use those atoms as a mixer, or just use the converter here and then implement many interesting schemes for the detection of weak signals that use direct detection or even photon counting. And in optical communication, it's been a topic of research using advanced detectors such as Dolina receivers in the most complex theoretical scheme that all employ photon counters. But with just a detector, yeah, it's a cool effect that yes, you can transmit information. So if you look around, there is a paper where people transmit a TV signal over the laser beam. Highly recommended. It's from the team of that I don't have this particular paper, but it's from sorry, just a second. Yeah, because it's I have the short citation here that I will just show, and this will be the last thing. Yeah, it's from the team at NIST here. So if you look at those guys, they also did some nice transmissions. Thanks.
Okay, great. Yeah, thank you so much. I think that's a great place to end. So yeah, as I mentioned, there will be a brief poll that Catherine will share just about the webinar to get your feedback. So here it is, and we'll give you about 20 seconds to complete. Okay, great. Well, yeah, thank you everybody so much. I would like to thank the audience for joining, and I would like to thank Michal for the great presentation. This was wonderful, and yeah, replay will be available soon. So thank you all.
Thank you. Thanks for coming.